welcome to the module. In this module we will see the other application of our operational amplifiers as a controlling. So, as we have already seen in the theory session, so we are going to design and implement an closed loop control system in this particular experiment. So, the whole idea of this experiment is to design and build a temperature controlled circuit using op amp as an on off controller and the proportional controller. So, when we recall our theory session, we have seen the importance and we have also seen in the applications of a temperature control in an industry as well as even in our research fields too. Now, based upon the criticality, how good that we control the temperature, the cost also matters. So, in this experiment what we do is that we will see how can we generate a temperature on a system. So, that system is nothing but a plant. So, what is the logic behind that, what is the design parameters and what is the logic behind that, how it is heating the plant, and we will take some temperature sensor on top of the plant because we require to measure the temperature, what is the temperature that is there on top of the plant. So, for that case, since the temperature is one physical phenomenon and since we are implementing a controller to control the temperature on the plant by using some analog circuitry, so we require to have an electronic input. So, electronic input is nothing but either voltage or current. So, we have to take a transducer or a sensor which converts a temperature change to an electronic output voltage. So, for that case we will take a temperature sensor which is of LM35. Now, we will see how an LM35 will work and what signal conditioning circuitry we require, why do we require the signal conditioning circuitry for the sensor before connecting it to the controller. Now, as we have also seen the importance and what different types of controllers that can be used and how complex the controllers are in the theory sessions, we will see how can we implement the controllers that we have discussed, that professor has discussed in the class using our operational amplifiers, their working, their designs and their practical, the results with respect to our experimental results, I mean simulation results with respect to the experimental results we will try to compare, and we will also try to compare with our theoretical results too. Now, when we recall, when we look back into our complete aim and objectives of this, so first part is that the main objective of the system, the main aim of the system is to bring the temperature to desired set point, right. So, when I say 50 degrees, the plant has to always maintain a temperature of 50 degrees. When I say 100 degrees, the plant has to be operated 100 degrees. So, operate in the sense it should always maintain, it should always control at a temperature of 100 degrees centigrade or at 50 degrees centigrade. Now, so in order to control it, we should know what is, our the specifications of our plant, how the plant will work like, right. We should also understand how we designed our plant, right, what input that a plant is required in order to heat the system, whether it is a current or whether it is a voltage, and how much input voltage that we have to give it, meaning power, how much input current or input voltage we require to heat the system, and what is the maximum current or what is the maximum voltage or what is the maximum power that the system can withstand without damaging it. So, once we know all these parameters, we can design our controller, our feedback controller or controller for maintaining the controller for maintaining or controlling the temperature on a plant. So, the objectives in this case is that to implement a circuit for heating the transistor, that is the major thing. So, we have to implement a circuit for heating a transistor, we will see, and we will also have to see how do we implement a controller to maintain the temperature of the transistor to a required set point. Got the point? But when I say required set point, so when I say required set point, which is nothing but we will always think about 50 degree, that is my set point. I always have to maintain the temperature of the plant to be 50 degree or 100 degree. But how an electronic unit will understand 100 degree when I say 50 degree when I say, so it cannot understand. So, in order to make the electronic system to understand our intention, the human intention, we require to do some mapping. So, or some scaling factor which converts our input temperature to input voltage, some kind of a sensitivity or some kind of a scaling factor has to be decided. So, now we will see one by one. So, we will take this particular objective to the last and we will see how can we use how can we implement this particular part. So, by using an operational amplifiers such that the major thing is that we need to bring the temperature to the desired set point by designing a basic controls with an objective of minimizing error for settling. That is the whole idea. So, when we look into our basic, so in order to implement the system, one thing is we should understand how a closed loop control system looks like. So, if you recall our theoretical session, what professor has discussed, this is the basic simple feedback system. So, in this case what we are going to do is that we will see how can we, so when we write in terms of a block wise, it is easy to see, it is easy to write a block, but when it comes to implementation, that too when we are putting on a hardware or when we are doing on a breadboard, we should understand the working and based upon that we have to design the system. We should understand the working of each and every block and we have to put it. So, before putting it we should understand what is the importance of this tool, right. So, when we recall what is the importance of the error detector, the purpose of an error detector is to compare the signal output with the system output, system input with the system output. So, what do you mean by system output? System output is nothing but what is the current temperature that is there on the plant, at what temperature the plant is operating at. System input is what user wants to maintain or what user wants to keep the plant at a point. So, let us say when I say the system input is of somewhere around 100 degrees centigrade or 50 degrees centigrade. So, in order to understand that, so considering, so like say the user wants to maintain the input as 100 degrees centigrade, but initially when you see the heating circuit or the heating circuit will be at room temperature meaning somewhere around 25 to 30 in between, it depends upon so where we are at. Now the temperature of the plant is 25, but the required temperature is 100 degrees centigrade. So, which are not matching, and moreover when we see the term 100 degree is our understandable temperature units, but electronic system does not understand 100 degree. So, we have to provide the input in terms of voltages. In order to put one particular factor, scaling factor, what I consider is I will consider 1 volt per degree centigrade, meaning when I say 1 volt per 10 degree centigrade, or 0.1 volt per degree centigrade is the scaling factor or sensitivity factor, meaning when you give the input as 1 volt, that means I am telling my system to maintain at 10 degrees centigrade. When I give the input as 5 volts, I am saying the set point of the system is somewhere around 50 degree. When I give input as 10 volt, that means the system set point is 100 degree, right. So, since electronic unit is only the understandable input to the system, the complete system, we have to convert the degrees in terms of voltages. So, this is what the factor that I am choosing it, right. So, this is clear. So, now this is clear for us. So, what I will do is that, so rather than saying 100 degree, so I will say 100 degree, if I do it, the input that I have to provide is 10 volt. The reason is that the factor is of the factor what I am considering is 0.1 volt per degree centigrade, right, 0.1 volt per degree centigrade. So, since it is 100 degree, so it is nothing but 0.1 by 1 degree corresponds to 0.1 volt. So, if it is 100 degrees, it will be 0.1 into 100, which is around 10 volts. So, if I apply input as 10 volts, that means I am saying the plant to be, this particular plant to be should be at 100 degree. Now, it will always start at 25 degree, because since it is a heating plant, right. So, if you see that, it will always be in degree centigrade, right. But how a system will understand, how this particular system will understand at what temperature it is at, if it is at degree centigrade, right. Physical parameter, when you see, the temperature is heat, it is not an electronic unit. So, we require some system, some transduction or some kind of electronic unit which converts the heat input into this electrical output. So, that is nothing but a sensor. So, if you recall the difference between the sensor and the transducer, a transducer which converts one form of energy into any other form of energy, any form of energy to any other form is called transducer. But whereas the sensor is nothing but any physical input, any form of input will be converted into electrical output change. Electrical output change. It can be resistance change, it can be current change, it can be voltage change, impedance change, anything. So, that the system which does this particular functionality is nothing but a sensor. So, even in this case, temperature is heat, where by touching only we will understand that. So, in order to give it as an input to the system, this particular system, we require to convert this particular system to electrical output by using a sensor. So, for that case we are using LM35. So, we will stick LM35 on top of our temperature sensor or on temperature plant, right. Now, why do we require the signal conditioning at this point? Of course, LM35 will also give an electrical output voltage, but it is not guaranteed that the output voltage that we get from the sensor is equivalent to the factor that we have decided here, right. It may or may not equal to. So, in order to understand how exactly this system works, we should look into the data sheet of LM35. So, when we look into the data sheet of LM35, one particular factor that we can see is sensitivity. So, the sensitivity of LM35 is 10 millivolt per degree centigrade. So, when we look into the data sheet, the sensitivity of LM35 is 10 millivolt per degree centigrade, meaning 1 degree gives me 10 millivolt, right. So, since it is at 25 degree centigrade, when I see 25 degree, I will get 250 millivolt, right. 250 millivolt meaning 0.25 volts, I will write, which is nothing but 0.25 volt. Now, if the sensor gives me 0.25 volt, since I am passing the input to this point, right. So, this is 10 volt, this is 0.25 volt. So, when it comes to realistic way, from the sensing point of view, 0.25 it is easy to understand, it is 25, but when it comes to with respect to the input, where the sensitivity factor is 0.1 volt per degree centigrade. So, since it is 0.25 volt, it is nothing but it is at 2.5 degree centigrade, right. So, which means that both the factors, the input factor, both the factors which are nothing but the input factor as well as the output factor, both are not matching. That is because of the sensitivity, this particular factor change. This is 0.1 volt per degree centigrade, this is 10 millivolt. Of course, we can also consider 10 millivolt per degree centigrade, but it is very hard to provide accurately such a small input voltages to the system, right. So, because of signal to noise ratio, because of the electronic section. So, but if you see it is easy to provide 1 volt 2 volt with almost negligible change in the output. So, that is the reason, rather than changing this particular factor to 10 millivolt per degree centigrade, we will convert this factor to this particular value. So, if I multiply with a factor of 10, so 100 milli, so to this 10 if I multiply, so what will be, if I multiply with that 10 into 10, 100 millivolt per degree centigrade, so which is 0.1 volt per degree centigrade. So, which is matching with this particular value. So, in order to provide this particular factor of 10, we require to use a signal conditioning circuit. So, in this module we will see how to implement the signal conditioning circuit for LM352, the design parameters, why we are using it, everything. Once we get a signal out of it, that has to be, that is the output is nothing but the feedback signal from the sensor will be compared with the input signal, Now, since it is multiplied with a factor of 10, you will get an output as 2.5. Now, what is the difference? If I want to see the error, when you recall what an error detector does, it does the difference between input and the feedback signal. So, when we do that, 10 minus 2.5, which is nothing but 7.5. So, the error signal is nothing but 7.5. So, how it is doing? We have to subtract the system input with the feedback signal, right. So, in order to implement that particular logic using operational amplifier, one way is either we have to go with a instrumentational amplifier or with a difference amplifier. So, either we can go with a difference amplifier or instrumentation amplifier, it depends upon which one you are going with. But if you go with an instrumentation amplifier, it may be little higher cost, but the input impedance on the CMRR will be really good. But if you go with a difference amplifier, even then that is more than enough for us in this application, since the signals whatever we are getting is not almost a common signal. So, it is more than enough for us to go with a simple differential amplifier rather than 3 op-amp based instrumentation amplifier or any kind of instrumentation amplifier at this application. So, to implement this error detector, one thing is we should understand how to implement difference amplifier. Right. So, now after implementing difference amplifier, it gives me 7.5 volts, right. Now we should understand how does a controller works, what different types of controllers that we are looking for, what are the functionalities of the controller, what is the logic behind the controller. So, we will go with on off controller, we will see how does an on off controller works in this case, what does the on off controller do and how a proportional controller does. Since we have already discussed in the theoretical session, as professor discussed in the theoretical session about proportional controller, on off controller, we will see how do we implement the strategy of on off, logic of on off and proportional controller using this particular op amp, and we will try to implement here. So, once the error signal passes the controller will take an action, how much amount of input voltage or input signal, which is nothing but manipulated variable, to be provided to the heating circuit, so that the system can quickly heat to the required system input. So, system output will be always matched with the system input. So, that call will be taken by controller, but that requires some kind of an user input. It depends upon what controller that you are using. That user input are nothing but the tuning parameters. So, how fast to reach, how much time I require to settle down, right. What is the overshoot that we are getting, whether such high amount of current is okay to pass through the system in order to have a quick response, quick ramp to the desired set input, is it okay to the plant or not. Everything will be decided by the tuning parameters of the controller, right. So, we will see how can we implement those controllers using operational amplifiers, we will design it. Then the controller will give one particular output, which is in terms of a voltages. We have to understand whether the heating circuit can take input as voltages or not. So, in order to understand, we also have to understand about the heating circuitry too. So, if I can implement one by one using operational amplifier, right, using operational amplifier, it is easy for us to understand the complete circuit, as well as in case if we are getting a problem at this point, we can rectify the problem and I can integrate with the complete system, and we can see the complete operation and controlling of the system. So, what we do is that we will build each and every subsystem, we will convert this complete experiment to different subsystems, will take one particular subsystem, will build it. So, similarly all other subsystems will verify the functionality with the theoretical, practical and experimental. If both three are matching it, then we will integrate everything together and we will see how the response will be of, right. So, that is a complete plan of our this experiment. Now, so one thing we should be keep in our mind, what is the input sensitivity or input scaling factor that we are using for the system, right. So, which is nothing but 0.1 volt per degree centigrade, that should be always we should keep in our mind, because since it is an electronic system we should always have to give in terms of voltages only. Okay. Now, so we will start with the simple error detector. We will start with the simple error detector, which is nothing but a differential amplifier. When we see, right, so this is a differential amplifier circuit, right. One input will be connected to the R1 R2 pair resistor pair, other input is connected to the negative terminal, which is input of R3. So, the output will be, so if you recall the working of differential amplifier, the output is nothing but V1 minus V2 into RF by R1, RF by R1. This is a case when if R1 is equal to R3 and R4 is equal to R2. Since in this case both R1 equal to R3, R1 equal to R2 equal to R3 is equal to R4. So, RF and R1 values are same. So, the gain of the system is 1. So, the V naught is V1 minus V2, that is what even we required, right. When we recall our system, we do not have to apply any gain, whatever the input I have, it has to be subtracted with the feedback signal and I have to get an output, that output we call it as an error, right. So, in order to give that I do not need any gain. So, since I do not need any gain, I am using all the resistance of same value. So, that may be the problem with instrumentation amplifier. So, few instrumentation amplifiers will have a gain starts from 5, the commercially available monolithic instrumentation amplifier IC, the minimum the gain that will have is 5. So, since it is not possible in this case, what we have to do is either we have to go with a high input impedance differential amplifier too, right. So, I understood how exact. So, we already know how does it works. So, let me quickly look into the simulation. So, in order to understand about the simulation whether it is working fine or not, what we will take is we will take different points. So, let us say I will take V1 and V2 and I will calculate V naught. So, V naught when you recall it is nothing but V1 minus V2, the input that I am applying at this point and this point, right. So, let me take one input as 10 V1 and another input as 2. So, that means 100 degree and 20 degree. So, what will be the V out? V out will be 10 minus 2 8 volt. I should get an output as 8 volt, right. So, this I am taking 8, this is 4. So, V out will be 8 minus 4 4 volt, 6 6. So, I will go with 8 in this case, I should get minus 2 volt, right, and 4 and 10 I should get minus 6 volt. Let me see whether I am getting these values if I design in a practical system. Now, in order to understand about the gain, what we do is that we will in order to practical as well as theoretically to calculate the gain as well as the CMRR value of the system, what we can do is that we can apply same signals at V1 and V2 and we will see what is an output voltage we are getting. So, we know that V out by the input voltage that we do which we connect is nothing but a gain of your system, right. When we connect the same signals, V1 plus V2 by 2 will be the common mode gain, because at this point we are taking V1 is equal to V2, we will get common mode gain. Now we will take different values of V1 and V2 and we will calculate what is an output and divided by V1 minus V2. This is nothing but our differential gain. Now if I want to calculate my CMRR, so CMRR is nothing but differential gain by common mode gain. So what are the gain that I am getting? This is AC and this is AD. This divided by this, if I do, I will get the CMRR of the circuit. We will see theoretically now and then we will compare with practical too. Excuse me. So to understand that, what I will do is that I will open a multisim. So let me create a circuit. So we are using multisim from so many experiments, so I do not have to explain about how exactly this works and what are all the different functionalities and different system that it has. So our only thing is that how do we implement it, that we will see. So we will connect according to our input signal. So what I will do is that I will take a 5 terminal, because the plus VCC and minus VCC are very much important to understand whether it goes to the saturation or not. So that is the reason I am taking this value plus VCC and minus VCC 2, and I will take some voltage sources, DC voltage, and I want to operate my system with 15 volts, changing settings to the input voltage to 15. So positive is connected to the positive terminal and other terminal should be connected to the ground. So I am connecting it to the ground. Now I have to take another voltage source, because op amp has to be provided with a two different voltage sources. This is not a single source, we have to always take two sources, two independent sources basically. So the negative of the power supply is connected to the negative terminal. So since negative 12, since it is the amplitude is 12, since the negative is connected here, the value is 12 minus 12 volts. So since we require minus 15, so this does our requirement. Now what we have to do, we have to connect one resistor at this point. So in order to not to have a mismatch between both this as well as our design in multisim, what I will do is that this is R1 I will consider, and this I will say 100K. In fact, you can also take any resistance value, but it should be all resistance whatever we use should be same one, but higher the resistances, right, more the input impedance of the system. More higher the resistances, more noise into the system. Noise is always proportional to the resistance value or resistance power for excuse me. So that is the reason we have to moderately select between 10K to 100K, but 1K if I select is, even we can select 1K, but it will have slight loading effect to the previous stage of your system, loading effect on the previous stage of your system. If I go more than 1K, 100 ohms, it will have more loading effect on the system. So in order to not to have that, we are considering somewhere around 10K to 100K. So in this case I am considering 100K. So I need to take one more resistor, and this is my R2. So this R2 part is done. So this part I have to connect it to the ground. So the ground terminal I have taken, I am connecting it here. Okay, and this part should be connected to here, and this part also connected to the positive terminal. So this is nothing but V1. So I will take one more DC voltage source, connect at this point, right. What I will do is that this I will make it as, the name of this I will make it as V4, because V1 notation we are giving it for the input value. So this I will make it as V1. Now so V1 is ready. So this value make it to 10, max is of 10 we are looking at, so 10, other terminal should be connected to the ground. So, I am connecting it to the ground. So, this part is done. What is the other part? The negative feedback and the negative resistance at the negative terminal. So, I will take R3 resistor. So, this is what R3 that we are considering it, and one more resistor that I have to take, which is R4, which should be connected as a negative feedback. So, I am connecting one here, one more to this junction, and other terminal to the output voltage, right. So, this point I have to connect another voltage source. So, just a nomenclature, just I will just slightly change the naming of the system here. So, this I will name it as V phi. So, whatever I take will be V2. So, I will take one more voltage source, this is V2 voltage source, and this part should be connected to the ground, connected to ground. Okay. So, this I will start from 2 volts. So, to understand what we have done, we have to apply 10 volts, 2 volts. Let me see. First, we will see the differential gain, then we will do the gain of I think we have considered the resistance R3 R4 differently, and let me do the same experiments once again. So, I will take V1, connect it here, and this should be ground, making it as ground. So, this should start from 10 volts. So, let me take it to 10 volts. Then I should take one more voltage source. So, I need DC. So, I will take DC, connecting it here, and this should be ground. Now, so we will start from 10 volts and this value at 2 volts. So, what are all values we have considered? One is 10, other one is 2, other thing is 8. So, when we see what are all values that we have considered, 10 to 8 4 and 6 8 4 10. So, we know that this is 8, 10 and 2 8, 8 and 4 4, minus 2 minus 6. We will see what values we are getting for everything, then we will list it out. So, let me run. When I run it, we are getting output as 7.9958, 7.9958, whereas when the input is 8 volt, I am making this as 8 and this as 4 volts. So, what is the output we are getting? 3.995. So, approximately or almost close, because we always consider 3.99 as equivalent to 4. So, it is also giving 4. So, let me take it as 6, this should be 6 volt, and this value should be of 8 volt. 8 volt. When I see the value is minus 2.0041. So, almost same 0041. Now, this I will take it as 4 and this I am taking it as 10. So, what is the value we are getting? Minus 6.0040. So, we got all the values. We will also take V1 and V2 as same values and we will see how much we are getting. So, we will take V1 as 5 volt one value and V2 also as a 5 volt other value. So, when V1 is 5 volt and V2 is 5 volts, actually the actual voltage should be 0, but as I told you it will be always at millivolt. So, when we see it is somewhere around minus 4.0811 millivolt. So, what about for other value? So, let me take the value somewhere around 10 volt and this also at 10 volt, should be almost same. Yeah, see when we see 10 and 10 Actually the value should be 0, but we got minus 4.1323 millivolt. Now let me put everything in graph and we'll put everything in our slide, and let us see what we get. What will be the CMRR value, right? And so when we recall, what values we got? V1, V2, actual output. So actual output is nothing but V1 minus V2. So here I will write V1 minus V2, no gain, because 100 by 100 will be 100k by 100k, it's 0. And consider this is simulation, V naught of simulation, output voltage at simulation, what is the value we are getting? So V1 we have considered 10, this is 2. So what is the value? 8 we got, right? When we do manual calculation, it is 8. What about the simulation? We got 7.995 volt. Then this is 8, this is also 4, this we got 4. So whereas this is 3.995. When we apply 6 and 8 as an input voltage, we got minus 2. Even here we got minus 2.004. What about here? 4 and 10, we got minus 6 when we calculate theoretical, and simulation we got 004, minus 6.004. And we have also done other experiments when both inputs are same, which are nothing but common mode signals, but actually speaking the output should be 0, but we are not getting 0, we are getting some value of 0.811 milli. And even it is almost same even when I am taking different voltage value of 10 and 10, which is of minus 4.1323 milli. Now if I want to calculate CMRR, first I should know the calculation of differential gain, then I have to calculate common mode gain. But how do we do differential gain? So the differential gain is nothing but output voltage that we are getting divided by common mode signal, divided by differential input signal V1 minus V2. Now when we see the theoretical value, so this is 8 for the first one and 8, this is 1. So we are getting differential gain as 1, right? So even for the second case, 4 divided by 8 minus 4, 1. So whatever, no matter what, for this particular set of values we will get the gain as 1 theoretically. What about the practical? This is theoretical. So AD simulation, when we see the value is V naught, V naught is 7.995 divided by 10 minus 2, 8. So when I calculate, I am taking calci, 7.995 divided by 8, 0.999, which is almost equal to 1, no matter what. I will take the next value too, I will take calci. So 3.995, so 3.995 divided by 8 minus 4, 4.998, so almost equal to 1, right? We are getting almost everything equal to 1. Now what about AC? Theoretically it should be 0, but practically when I see, simulation wise when I see, the value is minus 4.0. So how do we calculate? First let me write the formula, output voltage by common mode signal. So V1 plus V2 by 2. So what is V naught? Minus 4.0811 milli divided by 5 plus 5 by 2, which is nothing but 10 by 2, again this is 5. So minus 4.081 milli divided by 5. The value is, and I take a calci, 4.081 divided by 5, 0.81, how much? 62 milli, 0.8162 milli. So that means the value is 816, no volt, because volt by volt will be cancelled, right? 0.816 milli or 816.2. Now if I want to calculate CMRR, theoretical when I see, it should be AD by AC 1 divided by 0, which is infinity, but practically is it the same? Let me see, which is differential gain which is of 0.999 or 998 or 0.99 divided by 816.2. So, the value is, let me take a calci, 0.99 divided by 816.2, which is 0.0012. 0.0012. Now, if I want to calculate in dB, 20 log 0.0012. So, I will write it down here itself, 20 log 0.0012, which is equal to, so I will take calci once again, 0.0012 log into 20. So, which is 58.416 dB. Why I am eliminating minus? Because CMRR should be always mod of, or even in this case here we have a negative, and when we calculate minus we are getting minus is becoming positive, but CMRR generally mod of AD by AC. So, which is 58.4 dB for this particular type of op amp, right. Suppose if we are taking different op amp, I do not know what op amp that we have considered in the simulation, what make that we have considered. So, we have simply used the op amp that is available there, right. So, this is how we generally calculate the dB of our differential amplifier, but moreover, since we are not going to apply almost a common mode signal, but even if we apply, we are getting somewhere in the milli, since it is negligible. So, we can simply go with a difference amplifier itself. Now, how about for instrumentation amplifier? Why do not we look into that? So, what I will do is that I will take one more slide for instrumentation amplifier. If we recall the working of an instrumentation amplifier, so it will be somewhere, we will be taking 3 op amp plus minus one more op amp plus minus, right, resistor combination. So, this is R, this is R, this is Rg if I take, minus and plus connecting here, this here and this here. If I say this is V1, this is V2, right, and I should also have to have a differential amplifier here, plus minus, oh sorry, this is Rg, the output should be connected one here, one more here, and one more here, one more here. So, 100K, 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 4 resistance here, 1K, 1K. If I take the V0, so when we see V0 is nothing but 1 plus, generally V0 value is 1 plus 2R by Rg into V1 minus V2 is the equation. Just look into the instrumentation amplifier circuit, you will understand. Now, in this case what we do is that we will design the same thing and we will see for different values of V1, V2. Now, I will say this is VO1, this is VO2. What are the values of VO1 we are getting, what we are getting for VO2, and what about V0. So, I will take Rg as 2K. So, if I take Rg as 2K, the gain will be 1 plus 2 into 1K divided by Rg 2K. So, this is this one. So, the gain is 2, right. The gain of the system is 2. So, we will see what is the gain of the system even theoretically, and so theoretically we have calculated, which is 2. We will see with simulation. Now, so to the same circuit, what I will do is that I will take few more op amps. So, let me keep this aside. Okay. I will take simply 3 terminal op amps, it is more than enough. Okay. So, I have to choose different resistors, one here, one more here and one more here. Now, the output has to be connected at this point and negative terminal should be connected here, this 2 here, and this 2 here, whereas the negative terminal should be connected here. This is my V1, whereas this is my V2. This has to be connected. So, all the required connections are made. Let me run. So, so this is V01, this is V02, this is V0. So, I will take 2 more probes, connect at this point, 1 more probe at this point, which gives you V1, V02. When I run it, yes. So, when we see both are at 10, so we are getting minus 4.1323 milli. So, let me change 10 and 2, 10 and 2. So, 10 and 2, how much we are getting? At this point we are getting 12, this point we are getting minus 3.0152. Now, I will see. So, V1, V2, V01, V02 and V0. V1 is 10, V2 we are applying 2, V1 we are getting 12 and V02 is minus 3, V0 is 15, right. So, 10 minus 2 is how much? 8. 8 into gain of 2, 16, approximately 15 we are getting. Because why 15? It has gone to the saturation because of the voltage. So, what I will do is that I will decrease to 4. Now, second input is 10 and 4, 10 minus 4 is somewhere around 6, 6 into 2 12, I should get an output of 12. So, we are getting 12.056, right. Then, so this I will increase 8, this V2 to 4, let me take this as 8 and 4. So, 8 minus 4, the theoretical value should be 4 and 4 into 2. So, but we are getting 11.0996, sorry 11.996. Now, what I will do is that V1 I will make it as 4, V2 as 8, this 2 4, this I will make it as 8. How much we should get? 4 and 8 and 4, 4 and 8 we got minus 12.004. Let me apply the same signal, which is a 4 and 4 or 5 and 5, because that is the signal that we have used, 5 and 5. So, I got somewhere around, when I apply both 5 and 5, I got minus 4.0811 milli. So, this way we can even construct instrumentation amplifier and we can calculate our CMRR value for the instrumentation amplifier too, right. Now we will see what is our actual thing, right. So, we have calculated and theoretically we got the gain of 1. So, theoretically as well as we got practically we got gain as 1 and CMRR as 58.4 dB. So, no problem with this dp for us. So, we can go ahead with this instrument differential amplifier too. Now, what we will see, once we get error signal, right, once we get an error signal, another important to get an error signal is output from the sensor, right. So, output from the sensor in this case is LM35. As you already know why we are using LM35, as we have already discussed, we also discussed about the sensitivity. The sensitivity of LM35 is 10 millivolt, but the input sensitivity is 1 volt, sorry, this is 1 volt per 0.1 volt per degree centigrade, that is what the sensitivity that we are using. So, we have to match the input sensitivity with LM35 sensitivity, so that both factors will be of same unit. In order to match with that, we have to multiply the output of the sensor, which is LM35, to a gain of 10. Now, that means we have to amplify the sensor LM35 sensor output to gain, so that it will be my feedback signal. So, in order to do that, you can go with different things, but only thing is that input impedance and output impedance should be properly, the loading effect should be properly carried out, as well as the output should be of same phase, right. So, in this case, the whole idea is we have to get a gain of 10. Now, if you see this system, so when we recall this system, how does it look like? This is our inverting amplifier and this is our another inverting amplifier. Now, when we see this inverting amplifier, so how do we calculate the gain of inverting amplifier? Just recall our inverting amplifier circuit. When we see that, the gain is calculated as R2 by R1 in this case. So, R2 is 100k, R1 is 10k. So, the gain of the system is 10. So, that is what we require, but what is this input? Inverting input. So, that means if I apply 10 millivolt here, I will get 100 minus 100 millivolt, right. But what I require? I require plus 100 millivolt, so that the sensitivity will always match. Otherwise, there will be phase difference, because we are implementing error detector. Suppose if you implement a summation, here if I get a negative, so there somewhere, so finally we will get a difference between V1 and V2, but we are not doing that, right. We are implementing a differential amplifier there. So, that is the reason the phase output should be in a positive, right. So, because of that reason, the output of the inverting amplifier output, first stage of inverting amplifier circuit has been connected to the second stage of an inverting amplifier with a gain of 1. So, since the gain is 1, so no change in the amplitude output voltage, but there will be a phase, because it is also an inverting. So, we will get output as 100 milli. So, the problem is solved, but is this the only way to do it? No, we can also choose non-inverting amplifier, right, with 20k and 2.2k resistors. So, when we calculate, the gain will be approximately equal to 1 plus 9.08, which will be 10.08, approximately equal to 10k2. With a single op amp also we can do, but I have chosen in this way. So, it is not compulsory that you have to always go with the same wing, but only thing is that it should provide us the gain of 10. Now, what is the reason behind taking these resistances here? So, when we recall, if you recall our previous module discussions, we told that the requirement of the resistance at 10k and 100k are for offset, bias currents compensation, right. So, to compensate for the bias current of an operational amplifiers, if I connect R2 and R1 in parallel, so it can be completely compensated. So, that is the reason whatever the resistors that we are choosing here, R1 and R2, the resistors have been connected in parallel, so that it is also compensated for the bias currents too. Now we will see whether it is giving us a gain of 10 or not. So for that case what I will do is that first I will take sensor input as 1 volt, right. So since the gain is 10, we will go with the millivolts itself. I will take 100 milli. So theoretically when you calculate we will get minus 1 volt, here I should get 1 volt. Now I will take 500 milli, right, gain is 10, theoretically we should get minus 5 volt, and here it should be 5 volt. Now why do not we create a circuit in simulation and verify it. Okay. So let me go back to the simulation, right, and new file, let me save this. I am taking a new file, right. I will take an op amp, right. So 2 op amps in our case, so both the op amps. Now we have one resistor, this resistance we have considered as 10k, so let me change it to 10k. This is 100k we have considered, 100k. So let me connect the wiring from here to here, here to here, and this resistance we have considered as 10k and 10k. So I will take 10k resistor, one connect here, one more 10k here. Now for compensating the bias currents, what we are doing? We are also taking the resistors whatever we have chosen in parallel, right. So I have taken even the parallel connection of the resistances, connecting it here, one pair. So I also need one more pair, so and this pair has to be connected to the ground, so I have connected to the ground. So I will copy everything and paste it here. This has to be connected here, right. So both the paths are done. Now, okay. Now this is my input to the system, that is nothing but the sensor output has to be connected here. So consider as a voltage source, DC voltage, connecting it here and other terminal to the ground. So we took 10 milli, 100 milli. The reason is that more than that, suppose if I take 1 volt, gain multiplied by 10, it will become 10 volts, it may go to the saturation, almost close to saturation where I cannot apply any other thing. So that is why I am taking 100 millivolt. So let me measure the voltage at this point as well as at this point. If you recall, for 100 milli the gain is 10, we should get output as minus 1 volt. Let me run, minus 999.94 millivolts, which is minus 1 volt. Now after passing through another operational amplifier which is phase changer, so the negative has become positive. So this is working fine. So we will take another one, 500 milli, we should get 500 milli, right, minus 4.997 plus 4.997. So that means it is giving the complete system, the signal conditioning circuit whatever we have designed for LM35 sensor is having a gain of 10 and having the same phase, so that we can directly, the output from the signal conditioning circuit can be directly connected to the error amplifier. So we have seen this part, signal conditioning as well as differential. So we finished this part and this part. Now we will see the working of the heating circuit or the plant, then we will look into the controller part. Once everything is done, one by one we will see the breadboard or the PCB board that we have created for the complete experiment. We can see how exactly these are working, and finally we will demonstrate you the controlling output based upon the system input.